So a loss function is a way to quantify the utility lost by any of the decision rules above. The less accurate the prediction, the larger the loss. This method punishes the model for inaccuracies. This can improve the trained model for better predictions with future data sets. The punishment varies in intensity depending on how far off the prediction may be, but depending on how far off the model was. So this means that if we look at this line as well as this line, so for the first one, it's just a straight line, and these are the data points it has, and the blue line represents the predicted model that the computer made. So if we can see like the different dots or points or data sets are at different lengths from the actual trend line. So what loss function does is it assigns each of these distances a value, and again, like punishes the model for being inaccurate. So a better way of looking at this is if we look at this linear line, this data set is well predicted. This one's pretty good, this one's pretty good. But then we look at these two and they seem a lot further off than the other data sets. So then what it would do is assign these two dots a value, example 2, and just punish the model in order like to show that it's inaccurate. And over time, that trains the model to make better predictions for future data sets. So an example of this more visually can be, so on the right, you can see an example of loss functions in action. All of the blue and red points that are on the wrong side of the boundary are assigned a value of punishment. Theoretically, if any point was wrong by a larger amount, the assigned value would decrease. So if we look here, this is back to like the weather example we just saw. We saw that some of these points were in the wrong classes. So this is on the wrong class, so we assign it a value of 1. This is on the wrong class, so we assign it a value of 1, 1, and 1 again here. And since these are all off, that assigned value is seen as like a punishment by the trained model and knows for future predictions that like its current set boundary or trend line is inaccurate. And just one more thing to add on, this example only shows ones, but if this point right here happened to be blue, this is further away and more inaccurate from the line than the other points. So this could be assigned a larger value, such as 2 or 3, to show that its loss is a lot more significant than those that were closer to the actual boundary line. So that can just be seen here. The further the line goes, the higher the punishment will be. And this is with like the advertising and sales example. Overfitting. So with everything we just talked about, you might be wondering why the computer doesn't just create a nonlinear or just like a completely random line that fits all of its data perfectly, as we can like see here. But this is known as overfitting, and that is when a model fits the training data so well that it fails to generalize to other data sets. So keep in mind that data sets have to be generalized enough to take in a lot of data and predict the output. Overfitting ruins the purpose of the model itself. So when we create a model in machine learning, typically it's not just for one specific data set. We're using that model and just using that data set as like a testing point, and then we want to use that code or machine learning technique to apply to various data sets. So we want to make sure that our techniques tend to be generalized and we don't overfit, as seen with like the boundaries here. And the black line would represent a proper model. Like, yes, there are inaccuracies on both sides. However, that's a lot better than having a perfect line such as this green line, because if we try to apply this to another data set with like different classes and like different sides, this will be more inaccurate than the overall generalized black curve. So an example of this, so for example, in the left graph, a dot next to the red one at the bottom of the screen is likely to be rain, blue. However, with the overfitted model, it can be classified as no rain, red. So this is looking back at like a weather example. This day might not have had rain, so it is inaccurate. And if you overfit a model, the line would look something like this, which is super weird, not linear. It has no pattern at all. All it's trying to do is make sure all the data sets fit into the proper class. However, this really is a bad technique, because if we have another point or new data where like the unclassified point is somewhere here, it's likely to be rain, but it's going to get classified as not rain because of the overfitted model. And if we introduce new data, such as like new measurements of pressure and humidity, this model won't work well. So it's just better to stick with the generalized linear line. And if we look at the sales technique, instead of following a specific trend line, this overfitted model just follows a point from dot to dot, creating a very odd nonlinear shape. And this, again, won't work for good trend lines because if we're trying to extrapolate data, you can't just follow a line. Extrapolating this data would be near impossible because there's no line of best fit, and you can't just extend the axes to predict the future. Regularization. So regularization is the process of penalizing hypotheses that are more complex to favor simpler, more general hypotheses. We use regularization to avoid overfitting. So as it just said, regularization is just used to avoid overfitting, as we just discussed previously. So in regularization, we estimate the cost of the hypothesis function h by adding up its loss and a measure of its complexity. So what does this mean? So if we look at these three examples right here, so regularization is going to take in these three sort of boundaries that are set by the red lines and classify them as either underfitting, appropriate fitting, or overfitting. So if we look at this data right here, this is a linear line, and again, it's trying to separate two classes. However, we can tell this is a bit too inaccurate because there's a lot of X's on the O side and a lot of O's on the X sides. And if we go to overfitting, this is technically perfect because there's all the X's are on one side and all the O's are on one side. However, this won't work because it's not generalized enough, because if we introduce it to new data, this is not like okay in terms of a proper boundary, because it's just not going to fit all data sets, and it's, again, overfitted. So something appropriately fitted would look something like this. So it's a curve where the majority of the circles are proper, the majority of X's are proper with the exception of a few, but that's okay because since it's generalized, it will work with various data sets instead of being overfitted, but it's also accurate enough so that it's not underfitting. Okay, Scikit Learning or Scikit Learning. Scikit Learning is a library often used with Python in order to conventionally use machine learning algorithms like the ones we went over. So everything we just covered are different types of machine learning techniques that can be used to improve your code or use it to solve certain problems. Just always keep in mind that not all of these techniques are going to work with all types of problems, and you really have to think about which one you're trying to use. And there's a lot more techniques than the ones we went over. And Scikit Learning is just a library that's used in Python in order to help solve these problems. So when you're using machine learning, it's often not a use of like you're actually physically coding in a machine learning technique. It's more of just using a library, such as we can see here. So from the neighbors, so this is using the nearest neighbor classifications. So it's just a matter of importing that library and just making sure you know how to use it and that the problem you're using it for is proper. So this is a very important library, especially if you're like implementing any machine learning techniques into any of your code. All right, reinforcement learning. So reinforcement learning is another approach to machine learning where after each action, the agent gets feedback in the form of reward or punishment. So positive or negative numerical value. So this type of algorithm can be used to train walking robots, for example, where each step returns a positive number, reward, and each fall returns a negative number, punishment. This approach is similar to loss functions, but instead also gives positive feedback. So if we go back to loss functions, we saw that the more inaccurate one of the data points are in terms of like the class, we assign it a certain value in order to punish it. But reinforcement learning is a technique where instead of just punishing the data set, we also reward it for proper data sets. So you can honestly think of this sort of as like your pet. If any of you have a dog, if it follows what you're saying, you can reward it with some like food, or if it's not, you can sort of get upset at it and just like punish it and make sure that it knows that whatever it's doing is like wrong. So you can technically also do this with your data sets. So if we have like new raw data and we run this sort of algorithm where it's like a reward punishment system, it's a lot easier to get proper inputs and outputs, because instead of just telling the computer what it's doing wrong, we're also telling it what it's doing right for future reference. And in my opinion, this is the most effective way of splitting up data. It's just efficient. It's sort of like loss functions, but just like twice as effective because of the reward and punishment system. And this is just something it would look like. So if we have like an agent, it performs a certain action, it's in an environment, we give it like a state and like a reward, or just like punish it or something like that. That would make sure that the computer knows from like now on that this is like either a good thing or a bad thing, just to help separate data into different classes. Okay. Unsupervised learning, which is just clustering. We did mainly focus on supervised learning today. So in unsupervised learning, we're going to be focusing on this section, which is just clustering. All right, so clustering. So clustering is an unsupervised learning task that takes the input data and organizes it into groups such that similar objects end up in the same group. So this can be used, for example, in genetics research when trying to find similar genes, or in image segmentation when defining different parts of the image based on similarity between pixels. This method of unsupervised learning helps organize data. So if we look at the data on the right, we can see that all the data is sort of in clusters and could be like of different, it could just be like a different variable for each of these like clusters of data sets. And what clustering does is just puts it into its own specific categories in order to like separate them. So as we saw with vector machines, it uses the existing data points and creates set groups in this case just to separate it. So advantages of clustering. So clustering has a few distinct advantages where it can be scaled to large groups of data. So this is comparatively very large compared to like the other data sets we saw, where there's a lot of different points in data, but it's also very clearly split up. And it's also really easy to adapt to new examples or new data sets. So clustering is a smart and easy way to set up data groups in order for machine learning to occur. All right, so an example of clustering can be used in the real world as, for example, pretend that there are a group of basketball players who need coaching. Their attributes and skills can be split into graphs to show which groups of players should go together in what sort of training. So this can be represented on a graph as seen here. So these, both of these axes could be like a certain variable, such as like height and speed. And we split up the players into specific categories depending on how tall they are and how fast they are. And this, in using clustering, we can sort of like clearly segment each category into separate groups, which would, again, in this situation, help with coaching. Okay, so just a quick review of what we went over. So we went over supervised versus unsupervised learning. Within supervised learning, we went over linear regression, nearest neighbor classification, support vector machines, regression, loss functions, overfitting, regularization, scikit-learn, and reinforcement learning, while for unsupervised learning, we went over clustering. So just going back to this image after we like learned, you guys got introduced to machine learning. So these are the two main categories we focused on in clustering, as well as regression and classification. As you can see that there are many more aspects to machine learning that can be introduced, but I just started off with these since they are the easiest to sort of understand, as well as a good introduction into what machine learning is really like. So just as like a final sort of statement, machine learning is just used to make computer models smarter to help you solve problems faster and more efficiently. And it's a very useful tool, and it's very important in like today's world and like the future of how we're going to like start coding. Yeah, that's basically all.